Right. Good morning. Today we're going to demystify one of the cornerstones of algorithm analysis, recurrence relations. Think of them as the special language we use to precisely describe the performance of some of our most elegant and powerful algorithms.
So, here's our plan. We'll start with the fundamental problem, why we even need these things. Then we'll look at a really intuitive visual method for solving them. After that, I'll introduce you to an incredibly powerful shortcut, the master theorem. We'll put it to work, and then, crucially, we'll talk about its limits.
So, let's dive right in. We begin with the central question that brings us here today. How on earth do we count the work when a function keeps calling itself over and over? I mean, think about it. We can all count the iterations in a simple for loop. That's child's play. But things become far less obvious when a function calls itself. The work seems to multiply, to branch out, and our simple counting methods just fall apart.
And this illustrates the difference perfectly. For loops, it's direct counting. But for recursion, we need something more sophisticated. We need a mathematical model. And that's precisely where recurrence relations come in.
So what is a recurrence relation? Well, it's simply the language we use to describe the work done by a recursive algorithm. It's an equation that captures the total runtime by adding up two parts, the time it takes to solve the smaller, recursive pieces, and the cost of the work you do at the current step to stitch those pieces together. And the classic example, the one we'll use to make all of this concrete, is merge sort. It's a beautiful divide and conquer algorithm, and it's absolutely perfect for our purposes today.
Now, what's really fascinating here is how we can translate the algorithm's actions directly into this mathematical equation. Merge sort makes two recursive calls on lists that are half the original size. That gives us the 2tn over 2 part. Then it has to merge those two sorted halves back together, and that work is proportional to the size of the list, so we add plus n, and there you have it.
Right, now we've got our equation. How do we solve it? Well, our first method is a visual one, called the recursion tree. It's a fantastic way to build a picture of exactly where all the work is being done.
So, the recursion tree lets us see the cost at each level of recursion. At the very top, level 0, the work to merge is n. At the next level down, we have two subproblems, each working on n over 2 elements. The total work? 2 times n over 2, which is also n. This pattern is the key. The work at every single level of the tree is the same, n. And because we're having the problem each time, the tree has log n levels. So the total work is simply n work per level times log n levels, giving us a final complexity of O of n log n.
Now, the recursion tree is a fantastic tool for building intuition. It really is. But for your exams, when the clock is ticking, you're going to want a shortcut.
And that brings us to the main event, the master theorem. This is an incredibly powerful tool, a formula really, for solving a whole class of these divide and conquer recurrence relations.
Now, you'll want to pay close attention here. Any recurrence relation that fits this specific form can be solved with the theorem. Let's break down what a, b, and f of n actually represent.
First up, A. This is simply the number of subproblems we create at each step. So for merge sort, where we split the list in two, A was 2.
Next is b. This is the factor by which we shrink the problem size in each of those calls. For merge sort, we have the input, so b was also 2.
And finally, f of n. This represents the cost of all the other work, the dividing of the problem, and more importantly, the combining of the results. For merge sort, this was that linear n cost of the merge step.
Right, and this is the crucial point. The entire game, the heart of the whole theorem, boils down to a single comparison. You compare the work you do combining, that's f of n, with this other term, n to the power of log base b of a. Which one of those grows faster? That's it. That's the whole game.
And that comparison leads to 3 possibilities. Case 1 is when that n to the power of log underscore b a term wins. It grows faster. This means the work is top-heavy, dominated by all the tiny problems at the very leaves of the tree. Case 2 is the balanced case, just like merge sort, where the work is spread evenly across all levels. And finally, case 3 is when the combining work, f of n, grows fastest. The work is bottom-heavy, dominated by the single big merge at the very root of the tree.
Right, enough theory. Let's put this into practice with a couple of typical exam-style problems.
As you can see, it's just a methodical process. For our first example, a is 4, b is 2, and f of n is n. We calculate n to the log base 2 of 4. Well, log base 2 of 4 is 2, so that's n squared. Now we compare f of n, which is n, to n squared.
n squared is clearly bigger, so it's case 1. And the complexity is theta of n squared. Simple. Now for the second one. A is 2, b is 2, and f of n is n squared. Our comparison term, n to the log base 2 of 2, is just n. This time, f of n, n squared, is much larger than n. So this is case 3, and the complexity is simply theta of f of n, which is theta of n squared.
Okay, final section. The master theorem is powerful, but it is not a silver bullet. A good computer scientist knows the limits of their tools, so let's be very clear about when the master theorem simply doesn't apply.
So what happens when a recurrence just doesn't fit that nice, neat AF Tn over b plus f of n form?
Well, a recurrence like this, where we subtract a constant from n instead of dividing it, cannot be solved with the master theorem. It's just not what the theorem was built for. It only works for divide-and-conquer style algorithms.
For these sorts of problems, we have to fall back on other methods, like the iteration method, shown here. We just expand the relation again and again until a pattern emerges. You can see it here. After a few steps, it becomes quite clear that this is just going to resolve to a simple linear complexity, O of n.
And here is a very valuable slide for your revision. This is a quick reference table for the most common recurrences you'll encounter. I highly recommend you spend some time memorizing these. It will save you a lot of time.
So the key takeaway is this. Recurrence relations are the fundamental language of recursive analysis. The recursion tree gives you the intuition, and the master theorem gives you the speed. You now have the core tools to speak this language fluently and analyze a vast range of important algorithms. The only question left is, which one will you analyze first?